Okay, the next theorem is theorem 2.3. If x bar is the mean for random sample size from normal population with mean mu and the variance is sigma square, then the sample distribution of x bar will be also a normal distribution with mean mu and the variance of sigma square divided by n. Okay, so first of all, we define x is a normal distribution with mean mu and the variance is sigma square. And we know that mean of x is x bar, which is summation of xi divided by n. So now we want to prove this theorem, saying that the x bar will have the sample distribution also normal distribution with mean mu and the variance of sigma square divided by n. Because of x is normal, comes from the normal distribution, so x bar is also the normal distribution. How we can prove this? Okay, to prove this theorem, we should use the method of MGF technique that you have learned from the chapter 1 before this, the third technique, MGF technique. Okay, to prove this theorem, saying that when x is normal distribution, x bar also will be the normal distribution. Okay, because of we deal with the special distribution which is normal distribution, and you memorize the MGF for a normal distribution, so we can use the third method, which is the MGF technique, to prove that x bar is also the normal distribution. Okay, so how to start? By using the MGF technique. Okay, so now we want to find the distribution for x bar, which is m x bar t, right? Because we want to find the distribution for x bar. Right, we start with this, and we know that xi is a normal distribution having the MGF of E mu t plus t square sigma square divided by 2. Is it? Alright, so we start with this. The concept of MGF, it is expected of ET x. So now it will be ET x bar, right? Which is expected of ET summation of xi divided by n. Right? We expand this. You can have tx1 divided by n plus tx2 divided by n, right? Until txn divided by n. We also can write this as expected of E tx1 divided by n multiply expected of E tx2 divided by n until expected of txn divided by n. You have learned this in chapter 1. Alright, so you have familiar with this term, which is mx1 t divided by n. Why we put x1 here? Because we know that x is normal distribution, so we know the MGF for x1. We know the MGF for x2. Okay, so until mxn t divided by n. Okay, so we already defined the MGF for x, for normal, E mu t plus t square sigma square divided by n. So now here mx, here mxt, here we want to write mx1 t divided by n. So how to do this? Replace t here with t over n. So E mu t over n plus t over n square sigma square divided by 2. This one is for mx1. mx2 is also the same MGF. So it will be mu t over n plus t over n square sigma square divided by 2 until, how about this? It's the same like this. So how to multiply this? You will get n mu t divided by n, right? Because of you will add the index of exponent here, right? So it will be n mu t divided by n plus n sigma square t square over 2n square, isn't it? Right, so from here n and n here you can eliminate, n and n here you can eliminate. E will be E mu t plus sigma square t square over 2n. This is our last MGF for x bar. So according to the technique of MGF, the final solution here, the final solution of MGF, you compare this final solution for MGF with the other familiar MGF from the other distribution. So if you look at this, it looks like the MGF for normal E mu t, right? But with the different parameter. What is the parameter? Mu here, and here is parameter is sigma square. So here t square over 2, so it will be sigma square divided by n, right? So here is the parameter mu, parameter sigma square is the parameter mu. The parameter here is sigma square divided by n, because here t square over n, t square over 2, t square over 2. So the parameter will be sigma square divided by n. So from here, from this MGF, we know that x bar having the normal distribution with parameter mu, and the variance is sigma square divided by n. We proved the theorem 2.3. So we can write it as x bar also having the normal distribution with mean mu and the variance sigma square divided by n. This is how you find the distribution of the random variable that having the special distribution, right? Using the third technique, which is MGF technique. Okay, try to do this example. Example 2.4. If two samples from normal distribution population, by using the MGF technique, show that x1 bar minus x2 bar will be the normal distribution with parameter mu1 minus mu2, and the variance is sigma 1 square divided by n1 plus sigma 2 square divided by n2. It gives you the hint. Two sample from normal distribution population. So means that xi from normal distributions, sorry, x1 2, x1 from normal distribution mu1 sigma 1 square, and x2 also from normal distribution mu2 sigma 2 square. Okay, so now we want to show that x bar 1 minus x2 bar is normal distribution with the parameter here. So according to the hint, it's showing that mx bar equal to mx t over n power of n. Okay. So we can write it as m x1 bar, okay, equal to mx tn. Okay, what is the MGF for x1? Will be E mu1 t plus t square sigma 2 square divided by 2. Sorry, the second population is the second population, E mu2 t plus t square sigma 2 square divided by 2. So here will be E mu1 t plus t square sigma 1 square over, here t over n because of mx t over n. So you place t with t over n here. So here will be 2 n square, right? Because of here you replace with t over n. Alright, okay, and then power of n here, power of n. Sorry, it should be here n1 and n1, right? Because of the first okay, mx bar 2 will be e power of mu 2t over n2 plus t square sigma 1 square over 2 and 2 square power of n1, okay, will be mx t over n. So we should replace t here with t over n, so you look at this and this. Alright, so what we're gonna do is we want to find the distribution for x1 bar minus x2 bar. So we should start with mx1 bar minus x2 bar t, right? Remember the concept of MGF technique, ET x1 bar minus x2 bar, okay, so we can write it as expected of t x1 bar minus multiply e power of negative t x2 bar. Alright, so we can write it as mx1 bar t multiply mx2 bar negative t, right? Okay, mx2 bar, so it will be negative t. Okay, so we already have the mx1 bar t and mx2 bar t, so just replace here. So from here, this is the index power of n1, so we can eliminate with this. Okay, so lastly you will get mx1 bar t will be e power of mu1 t plus t square sigma 1 square over 2 and 1. Alright, multiply. Okay, here mx1 bar t, but here mx2 bar negative t. So here negative t, here, and here you will replace with negative t. T here you will replace with negative t. So it will be e power of t here replace with negative t. So you will get negative mu 2t plus t square replace with negative t, so you still get positive t square. Right, t square sigma, sorry, here should be sigma 2, right? So here will be sigma 2 square divided by 2 and 2. Okay, so we should multiply this exponential, so the index should be added. So you will get mu1 minus mu2 t. Okay, should add these two, right? Then factorize. Okay, plus factorize the t square over 2, right? T square over 2 here, t square over 2 here, we have t square over 2. So you will get sigma 1 square over n1 and plus sigma 2 square over n2. Alright, so this is our last MGF that we have. So this MGF looks like the MGF also for normal, but with different parameter. The parameter here mu1 minus mu2, and also the parameter for the sigma square will be sigma 1 square over n1 plus sigma 2 square over n2. So we can write it as x1 bar minus x2 bar, also the normal distribution with the parameter for mu is mu1 minus mu2, and the parameter for variance is sigma 1 square over n1 plus sigma 2 square over n2. So this is the way how you prove the distribution using the MGF technique. Like I said before this, you need to apply the technique of MGF as well in chapter 2.